Hello, everyone. Welcome to pre-lecture 18. This pre-lecture, we're going to be talking about titrations. So this was the technique we did last week in lab, and we're going to do again next week in lab, actually. And they are a method used to determine the amount or concentration of an unknown. And so typically, the thing we put in the burette is called the titrant. And then the thing that we were trying to find out down here in the flask would be the analyte. Okay. In order to determine when the number of moles of titrant that we add equals the number of moles of, of our analyte, we typically use an indicator to determine our equivalence point, right? With acid-base chemistry, which is of course the unit we're in, a strong acid or strong base is always used as the titrant to determine the amount of acid or base that is the analyte. And so of course, if we were trying to determine how much of an acid we had, we would titrate with a base and vice versa. Okay. To talk a little bit more about indicators, so the one we used in the lab last week was called phenolphthalein, that at more acidic pHs does not have any color, and then upon becoming basic would change to a bright pink, right? And that dependence is because indicators themselves are weak acids. So in this example here, this indicator in its protonated form has or a blue color, whereas once it's deprotonated, it would in its basic form have a red color, okay? And so an indicator's color will generally change within plus or minus 1 pKa unit. So if the pH of an indicator was 7.5, we would see a color change from 6.5 to 8.5 or thereabouts, okay? So in the situation above here, what would the color of our indicator be, or what color would the solution be if pH equaled pKa for the indicator above? And so think about that for a moment. The answer is, of course, purple. The reason it would be purple is because when the pH equals the pKa, we would have an equal amount our protonated form and our deprotonated form. And if you mix blue and red, you get purple. Okay. So we have a whole host of indicators that can be used across pH ranges. Essentially, the indicator you want to use will depend on what you want to, or what you believe the pH at your equivalence point will be. So if you look down here, phenolphthalein, the one we did last week, starts to transition around a pH of 8 and turns pink around pH 9.5. And so that is good for weak acids when at our equivalence point, the pH will be basic. And so let's talk a little bit more about that. And so again, the equivalence point is defined as the place where the number of moles of titrant that is added is equal to the moles of analyte in the original solution. So if we are titrating a strong acid with a strong base, we know that at the equivalence point, our pH would be neutral, pH would be 7, because the conjugate acid and conjugate base of both strong acids and bases do not have an effect on the pH, right? However, if we titrate a weak base with a strong acid, we know the pH should be below 7. Vice versa, if we titrate a weak acid with strong base, the pH at the equivalence point should be above 7. And we'll go a little bit over why that is more later in the lecture here. Another important place on the titration curve is the half equivalence point. And so this is when the number of moles of titrant that is added is equal to half the number of moles in the original solution. And so this is what we were titrating to last week in lab. It's when essentially our weak base and weak acid are going to be equal. And this is, of course, when our pH is equal to our pKa, because our log term with base over acid would cancel out, okay? So this is what a titration curve might look like if we collected data for the volume of NaOH we added and plotted it against pH. And so looking at this titration curve, are we starting with an acid or a base? And then are we titrating an acid or a base? And is the analyte strong or weak? So take a moment, pause the video, think about this if you need to. I'm going to reveal the answers now. So this would be an example titration where, say, we had HCl would be our analyte and NaOH would be our titrant. We know that because we start at a very low pH, meaning it's acidic, right? And then as we add more NaOH, we eventually reach our equivalence point, which is a pH of 7. And so we know that this should be a strong acid and strong base titration. Okay, the way we would determine the pH at various points, and we're going to have some practice with this in class, is before our equivalence point, we know we should have HCl in excess. So if we find that concentration of HCl or H3O+, take the negative log of that. That will tell us what our pH is. And then at our equivalence point, we know it'll be 7. After the equivalence point, we would figure out the amount of excess hydroxide that we have. We could take the negative log of that and then do 14 minus that POH in order to determine our pH, right? Okay, here's another example. So same questions. Is the titrant an acid or a base? Is the analyte an acid or a base? And is the analyte strong or weak? So take a moment, think about that, pause the video if you need to. I'm going to reveal the answers now. So this is a weak acid plus a strong base. And so if we think about how we would calculate things for, or pH values, I should say, for this, we know our initial pH could be found by just taking our concentration of HA, doing an ice chart, and finding our concentration of, concentration of hydronium. Between our initial pH and our equivalence point, we are in what's called the buffer range. And so this is where the pH is equal to the pKa plus the log of our conjugate base over our weak acid. We should know that we can use the Henderson-Hasselbalch equation in order to solve for that, okay? At the equivalence point, all that we have left then is our conjugate base. So this should be at a basic pH. We see here that the pH is above 8, meaning that is a basic pH. In class, we'll go through another example on how to calculate that. And once we are past the equivalence point, our pH is going to be determined by the amount of hydroxide that we have added in excess, meaning that essentially we just figure out how much excess hydroxide we have, take the negative log of that to determine our POH, and then can solve for our pH from there, okay? All right, what about this example? Same questions. Is our titrant an acid or a base? Is the analyte an acid or a base? And is the analyte strong or weak? Take a moment, pause the video if you need to think about this, and then we will go through it here. And so the answer to this is that we have a weak base, in this case, ammonia. We know it is a weak base. Well, first off, we know it is a base because we start with a high pH, which is indicative of a basic species. And we know it is weak as opposed to strong because our equivalence point is less than 7, right? Our equivalence point is about 5. And so that would mean that this is a weak base being titrated with a strong acid. And we could also tell that from the volume of HCl that we add there, okay? So here's another example for you. So question, is our titrant an acid or a base? Is the analyte an acid or a base? Or is the analyte strong and weak? And so this one looks a little bit different. Take a moment, think about that, see if you can come up with an answer for what this is. I will reveal the answers now. So this is a polyprotic acid, right? Where we are adding a volume of NaOH still. So we're titrating with a strong base, meaning that we're starting with a weak acid. And then at the steepest part of our slope, in 2 spots, we have our first equivalence point where our first diprotic species would be neutralized, and then a second equivalence point where our second species would be neutralized, okay? And so if you ever see essentially a pH, or rather a titration curve with multiple plateaus on it, that means it is a polyprotic acid. Okay. That'll be it for our pre-lecture for today. I hope that was informative. If you do have any questions, please let me know. I'd be happy to help out. Otherwise, I will see you in class. Take care.